Greetings, hello. This is week 5 of video B. All right. This is just the last lecture before the midterm. Of course, this lecture nor the last one will be on the midterm. This is just the next topic. We have to move forward. Uh, we're doing mathematical induction right now, which is an advanced proof technique that is universally applicable. It's been around me ever since I was in high school. I've used it for the past 500 years. And and then after that, closely related is recursion. So let's first just go straight to the presentation. So let's just go back to the beginning of this. All right. So here we are. Um, and you get the idea. I trip one domino and it trips the rest of them. It's more to it than that, but that's just a nice way of looking at it visually. We define the principle of mathematical induction here, which is actually equivalent to the well ordering principle. We talked about that earlier. And we'll try to, this only works for natural numbers with a set of positive integers. It doesn't work for, well, imagine the well ordering principle for the set of integers. It just doesn't work because there's no starting point. With natural numbers, it's 0. With positive integers, it's 1. For the set of integers, it's minus infinity. That's not a number. Okay. Clearly, it doesn't work for real numbers either. Okay. It works for the set of positive integers or natural numbers. And there's a relationship with recursion or recursive sets. So let's have a look at this. Here, learn these terms. This is an open expression, a summation or a multiplication. That's a big capital Pi is a multiplication. That is an open expression, just like a recursive set is also an open expression, which we will encounter later in this presentation. It's equal to this closed form expression. All right. And this is a geometric proof of it. Oh, you don't have to be memorize this. It's just obvious just by looking at it. It's an interesting proof, but it's geometric, and just like Venn diagrams, we don't use those for set theory, or truth tables. We don't use those for proving propositional logic either. As in this case here, we don't use geometric diagrams to make proofs. They're just not formal. They don't work to demonstrate that it works ad infinitum. All right. So this is the well ordering principle. As you can see, it applies to positive integers. We've seen this before. It's a very compact statement. We like that in mathematics. So there's a positive integer m for every positive integer n, such that m is always less than or equal to n. And so that works for any subset of the set of positive integers or for the set of positive integers itself. It shows you that there is a smallest integer, and it's well ordered from then on. And this holds for all positive integers, so it's the well ordering principle of natural numbers. So this is in words. What it says, if it's true for the base case, and then if you take an arbitrary step on, say, the ladder, if you want to express it that way, it's also true for the next step. So the kth step implies a k plus first step, and that's the inductive step, as it's called. It really isn't repeated applications of modus ponens. This is too simple, but for us, it's good enough, just to show you that it is not induction. It's an improper name for it. It is deduction. It's based on modus ponens for the large part, but it's more subtle than that if you're a mathematician. So here we go. As an induction axiom, well, yes, this is the proper way to define it. So there's a base case, and for all k, p of k implies p of k plus 1. This set here implies that the proposition is true for all n. Okay, that is the inductive proof schema. Here, the way we are looking at it as computer science people or whatever, not really mathematicians, we can think of a primitive rule. So there has to be a rule. It's a rule of inference, and it's an inductive rule. And so in this case, it is modus ponens, p of 0, and pk implies pk plus 1. Therefore, for all Pn. Okay, so this is like P implies Q, P, then Q. Do you see? It's modus ponens. But not really. Modus ponens can only derive finitely many instances, one step at a time. There's that AI assistant. I can't get rid of it. Well, I can, but I haven't done it. And while induction asserts a universal conclusion in a single finite step. So repeated applications of modus ponens is absolutely intractable, but in a way, that's what we're doing here. It has the form of modus ponens, but it has to be in an induction axiom set. All right. So what it really is, as far as we're concerned, this is what you have to know, is that once I get on to the how do I get rid of this thing? Hide. Hey, how about that? How do I get rid of this thing? Hey, hide for this session. Beautiful. Wow. I got rid of it. I feel so intelligent. So we can reach step one. That's the basis step. Then we go to the kth arbitrary step, and that is the inductive hypothesis that we can get there. The inductive step is to get here to the k plus first set. So here for the set of real numbers, positive integers, I should say, real positive integers, the truth of the first step, that's the basis step. We have to always do this. It must always be done. And here's where all the work is. First, we assume that the statement is true. So if we go back here, we would assume that this is true. The inductive hypothesis is that this is true. And from that, we derive the n plus 1 plus 1 over 2 step. Okay, that's the k plus 1 step. Okay, so p of k implies p of k plus 1 for all k in the set of positive integers. That's the inductive step. Some examples. You look this proof up and know it. Okay, obviously not for this midterm. So the sum of the first n integers, let's look at that. So I'm just going to go through these. Actually, they're very simple. There's no need for me to write things out at this stage. So let's just see. There it is right there. That's the thing that we tried to prove geometrically. All right. Well, we actually did show a geometric form. So here, this is the actual relationship we want to prove by induction. Base step, of course, it's a set of positive integers. So the base step is n equals 1. And the left-hand side, well, it's 1. And the right-hand side, 1 times 1 plus 1 is 2 over 2 is 1. So it works. Okay. Then, inductive hypothesis, we assume this is true. You must always state this. The base step, the inductive hypothesis, which is assuming what you want to prove is true. And then you take the inductive step, which is just where all the work is in all this business. And it is just simply algebra. That's all it is algebra. And this isn't a course in algebra. So I'm just showing you how to do stuff in order to really derive these things. That's algebra you should be able to do. And we don't have to waste time on it in this course. So we want to prove that this right here, these first n integers, or k integers in this case, it's true for n equals k. That's the k step on the ladder, if you will. So the first k numbers, we want to assume that it is equal to this closed form expression, k onto k plus 1 over 2. So we want to prove that it's true for n equals k plus 1. So that means 1 plus 2 plus all the way up to k plus 1. And what does that equal? Well, it's got to equal this inductive hypothesis that it equals this part here equals this part plus k plus 1, right? That's adding k plus 1 to both sides. So for factor k plus 1, you just do this algebra and you end up getting k plus 1 here, k plus 1 here. So you end up with k plus 1 times k plus 2, because that's k plus 1 plus 1, over 2. And that is exactly the formula for n equals k plus 1. All right. That is as simple as it is. So it's all in the algebra. And I mean, you can do this algebra, for God's sake. I mean, this is just rationalizing the denominator and then taking out a common factor and ending up with this, which is exactly what we're looking for. So how about the sum of even integers? Let's just keep doing this. So we want to prove that the sum of the first n even integers, okay, well, that would be 2 plus 4 plus 6 all the way to 2n equals n onto n plus 1. So, obviously that follows from this here, from this expression. You can see because it's a factor of 2 involved with just, taking the even integers, which cancels with the 1 on the bottom here. And you're going to end up with this over here for all n. So for the basis step 1, well, what do you have here? The left-hand side is 2. That's the basis step. And 2 times 2 plus 1 is 3. 2 times 1 is 2. All right. For all integers greater than 1. Okay, so that's this is for all n. Okay, so we're starting with 1 here. Sorry. We're doing this for the set of positive integers. So that's for all n greater than or equal to 1. You may be surprised to see that we don't start at 2. Of course, it is 2 for the basis step on this side, but you still put 1 in here on the right-hand side because this is for the set of all positive integers. So 1 times 1 plus 2, 1 plus 1 is 2. 1 times 2 is 2, so 2 equals 2. So the basis step works. Once again, this is the first object in the basis step because it's the first element in the sequence. But over here, we put n equals 1 because this is for a set of positive integers. All right, so it's just that simple. So the inductive hypothesis is that we assume that this is true. We assume this statement is true. The inductive step is we want to show that this sum here plus 2 times k plus 1, that's the next step. Okay, so we have that here equals that k plus 1 step plus 2k plus 1. Okay, so we're adding 2k plus 1 to both sides. That's all we're doing by showing the next step on both sides. We want to prove that we can go from k to k plus 1. And so we have the first k steps, and here we have the next step, which is 2 times k plus 1, obviously. And here we just simply have that k plus 1 from adding it to the 2k plus 1. Sorry, the inductive hypothesis is this plus 2 plus k, 2 times k plus 1 on both sides that you added to both sides. This is the inductive hypothesis that it's true. This is adding the kth step to both sides. This equals this. You can see it right here. And this is what we have right here. Okay. And so this right here, we assume that equals this, and we add to the k plus first step after that. And you factor k plus 1 out. Now you just do some simple algebra once again, and you get exactly the step, okay, for k plus 1. So that would be k plus 1 onto k plus 1 plus 1. And so that is this baby right here. K plus 1 times k plus 1 plus 1, which is exactly what we're looking for. K plus 1 onto k plus 1 plus 1. So simple algebra. All the work here in induction is the algebra. Okay, sum of squares, 1 squared plus 2 squared, all the way up to n squared equals this thing. Now, you can just work this out as well. It's the same thing. There's nothing new here. Because it's just algebra. And I don't want to go through the algebra with you and waste time with that because you can all do the algebra. So the inductive, the base step is, okay, 1 equals 1 times 2 times 2 plus 1 is 3, is 6 over 6, so that works. Okay, 1 times 2 times 3 is 6 over 6, which equals 1. Base case works, no problem. Inductive step. Well, we want to show that this equals this for the kth step on the ladder. Now we want to show that we can derive k plus 1. Never mind these big brackets. That's something I just can't get rid of with Word, okay, for this particular setup. We want to prove the formula is correct for n equals k plus 1. So here what we're doing is adding, okay, that bracket should match this bracket here. So we're adding k plus 1 squared, okay, and here, for all where you see n, we're putting k plus 1, okay? So k plus 1 times k plus 1 plus 1 plus 2 times k plus 1 plus 1. You see that? All right. And now we just, that's what we have here, and we do a little bit of algebra, factoring k plus 1 out from both sides, and simplify the bracket. Again, this is just algebra, and we've proven it correct, okay? We've proven it correct, okay? So substitute back, left-hand side equals the right-hand side. So there we have it. So this is just simplifying the bracket and then substituting back And we get this thing, which is exactly what we're looking for, proving this for all positive integers n. Okay, double factorial formula. This is an interesting one. So 1 times 3 times 5 all the way to 2n minus 1 equals this crazy looking thing right here. So the base case is 1. 1 equals, well, 2 factorial over 2 to the 1 is 2 times 1, okay, which is 2 over 2, which is 1. Okay, that works. Now the inductive hypothesis, assume this is true. Assume this is true. Then using an inductive hypothesis, we use this. The inductive hypothesis says it's that times the next k plus first step, which is this done to both sides, right? To make the equation valid, that's this equation, both sides multiplied by 2k plus 1, right? So that's the left-hand side, which is correct and fully explicit. Expand the right-hand side, factorials. So you can use the 2k plus 1 plus 2 equals 2k plus 2 times 2k plus 1 times 2k factorial, obviously. And k minus 1 factorial equals k plus 1 times k factorial. So k plus 1 factors out. We get the right-hand side. And that simplifies to this right-hand side, which is exactly what we were looking for. So this is true. You can see that it's true right here. Yes, it's absolutely right on, okay? That's 2k plus 1 times 2k factorial, which is 2k plus 1 factorial, okay? It's 2k plus 1 factorial, 2 to the k plus 1 factorial, okay? That's what we've derived here, okay? Whew. So that is how you prove this double factorial formula. I don't think you'll find that in the book. That's something I picked up elsewhere. How about geometric series? Everybody knows what a geometric series is. This is sort of a, if you've taken calculus, geometric series is converge. Harmonic series doesn't. 1/2 plus 1 plus 1/2 plus a third plus a quarter. So harmonic sequence does not converge. Geometric sequence does. So we want to prove that this is true, that the sum of these terms all the way up to r to the n equals this closed form expression, r to the n plus 1 minus 1 over r minus 1. And that's true for any positive integer, r not equal to 1, obviously, because you can't divide by 0. So the base case, obviously, it's 1 over here. And this thing is 1, r squared minus 1 is r minus 1. And so you get 1 here. R to the 0 plus 1 is r minus 1, okay? So it's true, the basis case holds. The inductive hypothesis is to assume this is true. Now we want to get to the k plus first step. So consider this term with the added k plus first term. And so that should equal this is the inductive hypothesis plus r to the k plus 1. You're adding it to both sides, this side and this side. This is the left-hand side. This is the right-hand side. And so now you pull over the common denominator, r minus 1, and simplify. What do you get? You simplify the numerator. Just do this algebra yourself, and you can see it's obvious. We're going to arrive at this conclusion for k plus 1. So it is true. We end up with r to the k plus 2 minus 1 over r minus 1. That's this right here. So the sum is exactly what we were deriving in the first place. Now, this is pretty good. This is something we didn't do in chapter 3, which is function dominance, okay? You'll learn that in 225, okay? And 225, okay. Why is this not lining up? So this is, for example, if you have some function, I don't know, like x squared, and you have another function, some other polynomial, and they cross over at this point, okay? From here on, if these are polynomials and this is a higher order polynomial, this is a lower order polynomial. This is a higher order. It goes up more sharply. That you can have a situation where for all values of x greater than this crossover point, this function dominates this function. It's called we it's called in God. It's what is going on here? Okay, it's called exponential versus factorial dominance in this case, and it is for proving that certain classes of function behave a certain way. We classify functions as linear, as constant, as polynomial, and as factorial, exponential, and factorial. So, for example, this is what we would have learned in Chapter 3, which I just have omitted now because it's in 225. You'll learn all about this there. Yeah, that's good enough for now. So let's just do it. So for integers n greater than 4, that's kind of like what we decided here with the crossover point, n factorial clearly grows faster than this exponential. It does, but it does after a certain point. N is greater than or equal to 4. That's just how it is. So we want to prove that for n greater than or equal to 4, n factorial is greater than 2 to the n. So proof by induction, base case n equals 4. 4 factorial is 24, and 2 to the 4 is 16. So 24 greater than 16, base case holds. Okay. Induction hypothesis, that's this. The kth rung, you can run to the k plus first rung. So this is the kth rung. Induction step proof is good for k plus 1. So k plus 1 factorial is greater than 2 to the k plus 1. Okay. Now we add k plus 1 factorial to both sides. Start from the left side. This is the left side. We multiply by k plus 1 factorial, and that's both sides. Okay, so if we multiply this by k plus 1, then it's k plus 1 factorial, is it not? It just goes into the factorial. K factorial times k plus 1 is k plus 1 factorial, and this is 2 to the k plus 1. Now, here's a trick. There's a trick that, so we've got k plus 1 factorial greater than k plus 1 times 2 to the k. So there's a little trick. We want k plus 1 times 2 to the k to be greater than 2 to the k plus 1. So that's k plus 1 times 2 to the k is greater than 2 times 2 to the k. That by introducing this 2 right here, we still maintain this inequality. All right? That's the little trick. All right? Which implies 2k plus 1 is greater than 2. So the little trick here is we've got this, and that implies that this holds as well. Now, all I've done is modify the left-hand side. We've pulled out 2 from the exponent. 2 times 2 to the k is 2 to the k plus 1. So far, so good. Now, this is the trick. Since for k greater than or equal to 4, k plus 1 greater than or equal to 5, and clearly k plus 1 greater than 2, k plus 1 factorial is greater than 2 to the k plus 1. That holds, and so it's true. So we had this little trick here, which is right here. For 4 greater than or equal to k, k plus 1 is greater than 5, all right? And so that point right there means that this holds, okay, which is what we arrived at right here, expanding this thing out with the 2 right there, okay, you see? That's what the 2 is good for, and that's what the k plus 1 is good for. So 2 to the k, 2 to the k on this side, the k plus 1 and the 2 are the things we have to hold the inequality with. Do they hold? Yes, of course they do. For k plus 1 greater than 5, okay? Okay, so that is proving exponential dominance greater than 4, greater or equal to 4, up to infinity. So the factorial dominates the base 2 exponential function. Proven. This is for the. I kept the slide in here. You can look at it if you want. That's mostly applied to is a to the n less than n factorial. Okay, So this is just another one, factorial dominance, but it's a little more complicated. It's mostly useful in chapter 3. So just ignore this slide right here, okay? Here's a good one, divisibility by 3. Okay, we introduced this, of course, in chapter 1. Chapter 1 we're doing proofs. So it looks like this. The basis step, if n equals 0, then n cubed plus 2 to the n equals 0 plus 2 times 0, which equals 0. So it is divisible by 3. Induction, we assume that this is true. Let's see. Here, let's just look at it right here. No. We're going to just keep doing this. These are these divisibility problems. Inductive hypothesis is just, again, assuming this is true. And then we want to prove it for the next step. And so that's n plus 1 cubed, and 2 times n plus 1 in terms of this inductive hypothesis. So we do some algebra, as always, and we end up showing this case right here. We derive this case, which is what we're looking for. We want to show that we can show that this is good for k plus 1 cubed plus 2 times k plus 1, and we indeed have done that. Where is it? Yes, here. Okay, and so 3 with that is divisible by 3 clearly. Okay, here we know that's the inductive hypothesis. We've assumed that this thing is divisible by 3, and so that is divisible by 3, and this factor right here has a 3 in it, so it is divisible by 3. Do you see how we did that? The inductive hypothesis is this part, and we know that if we assume that it's correct, that it's divisible by 3, and the way we've factored things out is to produce a 3 in front of this polynomial, and so that both terms are divisible by 3, end of proof. So you've got to know the direction you're headed with these problems. You know, practice makes perfect. Well, not perfect, but close enough for this course. Here's another one. Claim for all positive integers n that 8 divides 3 to the 2n minus 1. Or equivalently, the same way of stating this is 3 to the 2n is congruent to 1 modulo 8. All right. Base case, n equals 1. Well, this is certainly true. 3 to the 3 squared minus 1 is 9 minus 1 equals 8. So since 8 is divisible by 8, the statement for n holds. Remember what this means right here. 8 is divisible by 8, okay? Right, 3 squared, 9 minus 1 is 8. There we go, okay. Just had a brain fart. Inductive hypothesis. We assume this is true. There it is. We assume these both are true. The inductive step is we want to put a k plus 1 up there for the k. And we start with this and simplify, and we get this right-hand term. So 9 times 3 to the 2k minus 1 equals, okay, the right-hand side. Well, no, we're just factoring out. Factoring out the 9. Okay, because this is minus 1. So by putting that 9 here, it's plus 8, you see, by putting the 9 in there. Factoring the 9 out, that means we add, instead of minus 1, add 9, and you get 8 over here. So that, again, you showed the inductive hypothesis 3/2k is divisible by 8. Clearly it is, okay? That's what we wanted to find here as far as that's the remainder, okay? So it's cyclic about the remainder 8. And once we've showed that, we've proved that this statement is true for all k plus 1. All right. Yeah, I know I've gone through these pretty quick, but it's all algebra, and I don't want to do algebra for you. You know, I'd rather just show you how to do these things. That's the best way. Practice makes perfect. And like I said, all of the work, this one's a particularly difficult one because it's about modular arithmetic. Listen, I promise, modular arithmetic is already difficult enough. You know, in chapter 4, we've got our hands full there. I will not give you a proof by induction of modular arithmetic or of congruences. I won't will not give you a proof like that. All right. So you heard it here first. In fact, the test is already made. you've listened to me throughout this series of lectures, you'll know exactly what's going to be on the test. Not pulling any fastballs. I expect very high grades from all of you. Okay. So all of this comes down to algebra. It's always the same. Okay. It's you do the base case always. Here's an example of why you should do the base case. You don't have to read this whole thing, but what happens is, okay, you want to establish the validity of this statement right here. So we go directly to the inductive hypothesis, and we try to take the inductive step, and it doesn't work. Well, we would have known right away because it's not true, and the basis step would have showed it. So we did all that work for nothing. If we would have done the basis step, we would have known that the equality is invalid. Okay, so this is just always do the basis step. Always do it. Okay, proof of the binomial theorem. Well, it's funny that it's here. We haven't had the binomial theorem yet, but let's just say there it is. This is in chapter 6. But, why not? This binomial, as opposed to a monomial, which is x to the n, this is a binomial, x plus y to the n, equals this sum, this open form, which is equal to these binomial coefficients times these decreasing powers of x and increasing powers of y. Okay, so that's the binomial theorem. So I want you to go through this yourself. I'm not going to go through this with you. I always make students, this could be on the final exam, and I've given it to you. You just have to go through these steps. Of course, that's the basis step. Then you presume the inductive hypothesis. You can see that that's a little different from what I showed you earlier, but these two are equivalent. These two statements end up being equivalent. You'll find out in chapter 6. See, it's n minus 1 minus k, x to n minus 1 minus k, and here it's just x to the 1 minus k to the y to the k. So you can see that they're different. N minus j, here. I should have been here. This right here is just a equivalent way of stating the formula because these binomial coefficients are symmetric. You'll find out through Pascal's identity. So I'm showing you this to you early. I don't want to really go through it because this is something you need to work on after chapter 6. So to take the inductive hypothesis, okay, and so we know that we can take the binomial and factor out an x plus y. So that equals this by the inductive hypothesis. That's what that means. And then we use the distributive property across these. So we want to make these summations match up. That's the whole point. So there is a distributive property involved here, right here. You can see that. We've got a factor right here. So it's this applied to this. And so here we've got x to the n minus 1. And once we've factored in this x, you have x to the n minus k, and minus 1, minus k. Okay, so we've shifted, we've used the distributive rule by applying this to this summation. And we get these two sum terms, okay? Obviously, both involving the x going into here and the y going into here. Then we shift the indices. See, we're going to n minus 1 here. So we make a common j plus 1 substitution, and we end up having the summations match. They still match. And what am I doing here? I guess we're just doing this implicitly. Common j plus 1 terms get clumped together. And here we make a variable change, k equals j plus 1. And we match sums. Now, that's the whole point of this, is to be able to, sum of the sums is the sum of the sums. And so we're arranging things. So first of all, the sums match, and we can combine these exponents in a nice way so that we can come up with the second and fourth terms are from Pascal's triangle. So that's what's missing here. What you don't see is these binomial coefficients are related to each other through Pascal's identity. So this is something you don't need to know until we've done chapter 6, okay? But I want you to come back to this. All right, that's the whole point. Come back to it. So Pascal's identity is this right here. These two equal this coefficient. These two, the sum of these two binomial coefficients equals this binomial coefficient, and that's how we end up proving that we could get to the k plus first step. All right. Okay. Okay, never mind this. This is for later. So the principle, this is for when you get to chapter 9. 6, while the principle of induction is a very useful technique for proving propositions about natural numbers, it isn't always necessary. Okay, we've already done proofs with positive integers in chapter 1. For example, binomial theorem was proven without the use of mathematical induction. We could prove it using a combinatorial argument. That's what you'll see in chapter 6. Okay, there are proofs that we've seen, and there's also combinatorial arguments. There's element argument method of set theory, and in combinatorics, there's the combinatorial proof, and it's a little hard to catch on to. Here's a nice visual problem. So let n be a positive integer, show that every 2 to the n by 2 to the n checkerboard with one square removed can be tiled using right trimanos. That's a right trimano. So this is the basis step. Of course, it works. The basis step is just simply having one right trimano. So that's a 2 to the 1 by 2 to the 1, which is a 2 by 2 checkerboard. Okay. Now you go to the next one. So 2k plus 1 times 2k plus 1 instead of 2k plus times 2k. And so from this we can go up a factor of 2, and we have a how do we do it here? If it's got a remember, it's got to be, you have to have a defective checkerboard with one square removed, like this. And so here is a 4 by 4 with one square removed, and all we have to do is put a trimano in the middle, and that's showing that we can get from the kth to the k plus first step visually. This isn't a proper rigorous proof, obviously, because we only showed it for one step. We didn't show it for k to k plus 1, but you get the idea of how things work in terms of visual cues and so forth. Okay, that's enough of that. What a nice graph. So as you see, we didn't have to derive anything so far because it's just algebra. There's just algebra there. Let's do recursion now. So let's finish this chapter. Here we go. Get rid of that. Get rid of this. So now mathematical induction leads directly into recursion. This is still part of chapter 5. So that's a recursive picture. It's a picture in terms of smaller sets of itself. Okay, so it's a kind of a silly thing when you use pictures, but it is recursively defined. So recursion occurs when a thing is defined in terms of itself or of its type. Generally, in computing science, it's a solution method where the solution to a problem depends on solutions to smaller instances of the same problem, as opposed to iteration. Iteration is a different thing altogether, but they both accomplish the same thing. Iteration itself or of its type. So you know what iteration is. Well, everybody knows who programs. So recursion is related to iteration. And so you can see here, it's a method where the solution to a problem depends on solutions of smaller instances of the same problem as opposed to iteration, which goes the other way. Okay. And we'll see both of those in this presentation. So here's a recursively defined function. Classical example, n factorial equals 1. This is the recursive set. 1 if n equals 0. That's how you get started, just like induction, it seems. And n minus 1 factorial times n if n is greater than 0. So that is a recursively defined function. This is the recursive set. This is a recursive set. If you have some variable x at time t plus 1, which equals a constant k, which is positive, times a variable x, the same variable at an earlier time t, all right? So this process requires an initial condition, x sub 0, to get the process going, and you end up being able to recursively, this is a recursive set, and you can generate the entire series this way. This is called the well, this is just an exponential set right here. This is just exponential. You know, if k is 2, each iteration it doubles. So this is just exponential growth described in a discrete way rather than in calculus. So, oh, what's that doing here? I didn't take everything. Oh my God. Okay, I've got to fix this again. I thought I took these out. Oh God. They keep creeping in. I just don't know why I can't get rid of them anyway. Okay, all right. Recursively defined sequences. I'll take care of that and post it again. I just don't get it. I took them out. You know, obviously I've got parallel PowerPoints go at the same time. I mean PDFs. So recursively defined sequence is the Fibonacci sequence. Fibonacci sequence is classic. It's seen throughout nature. So here's the classic way of looking at it: reproducing rabbits, reproducing pairs at least 2 months old, young pairs less than 2 months old. So month 1, 2, all the way up, reproducing pairs. Well, we only have 2 young pairs right here, and we have to wait until they're at least 2 months old. So that's the 3rd month. Okay, so now we have reproducing pairs and 2 young pairs they have reproduced. So here we have total pairs 1, 1, 2. If we keep going, 3, 5, 8. That is the Fibonacci sequence. And how is it defined? 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 5 plus 3 equals 8. So it is a second order recursive set. This was a first order recursive set. It only needs one initial condition. This is a second order recursive set. There it is right there. I thought I said go away. Hide from this session. Hide. Okay, recursive set. We begin with 1, F1 and F2 being 1, like right here. And then the nth recursive member in the sequence is the sum of the 2 previous terms. That is the Fibonacci sequence. And we see it everywhere. On an introductory slide I gave you, you saw that green spiral-looking plant. That's this Fibonacci spiral. You see it everywhere. There's all kinds of almost cult followings of the Fibonacci sequence, looking for it all throughout nature. In fact, the golden ratio comes from the Fibonacci sequence, from the analytic solution to the recursive set, and it has this funny number in it called phi, which is how you define, which is the golden ratio. And we find the golden ratio all throughout nature. You've seen it. Here, this is that plant we talked about. So you can see the Fibonacci sequence 5, 8, 13, 21, 34, 55. And this is exactly the spiral pattern found here in galaxies and so forth. Here's the so-called biological basis. This is just for your interest, where you can see the golden ratio is everywhere. Look at this. The golden ratio just appears almost everywhere in nature. Okay. Nobody really has an explanation for it. So here, the Fibonacci sequence, we can see what it is. And we've got these 1, 2. If we sum them, we have another sequence 1, 2, 4, 7, 12. Okay, 1, 2, 4. What are these numbers? That is, what is Fibonacci F1 plus F2 all the way to Fn? This is really a bad slide. I don't know what happened to it. This is really bad. So what's happening here is this is this sequence that we've just defined right here. You can see actually this 5 relates to this 4, this 3 relates to this 2, this 2 relates to this 1. Okay, that's how the sequence forms. So that's the polynomial that polynomial sequence that we're coming up with. F1 plus F2 plus all the way to Fn equals Fn plus 2. What is that? Minus 1. Thank goodness. Minus 1 for all n greater than 1. So we proved this by induction. So this is I'm going to have to reproduce this slide and give it to you Again, I don't know what happened to it here. This is just a bad reproduction. And the notation is really bad too. I should have fixed this a long time ago. But anyway, what we're doing is, all we're doing here is we already know what a recursive, what a recursive sequence in terms of Fibonacci is. But now we come up with a different sequence by just summing all of these Fibonacci numbers. And we get this new series, 1, 2, 4, 7, 12. What is that relationship? We're going to assume, that's what we're doing here, is assuming that it's this, because it looks as though the sequence comes in terms of this relationship, f of n, this sequence here equals fn plus 2 minus 1, okay? So 5 minus 1 is 4, 3 minus 1 is 2, 2 minus 1 is 1. So that's the pattern that we have come up with as a proposition, and then we prove it by induction. You can go through this when I give you a revised version of this slide, because this is just another proof by induction. It's very easy proof. I'll show it to you later when I actually redo this slide. It's too hard to look. See example. I've got to take this out too, because not doing. Okay, so this is good. Fibonacci is really good. I'm going to, when we start doing lectures again after the midterm next week, I'm going to go over this again, and I will show you some more examples of proofs by induction for recursive sets, especially Fibonacci. There's tons of them. Here, now the Tower of Hanoi. This is a very, very a well-known problem. Of course, it goes back hundreds of years. The objective of the puzzle is to move the entire stack to another rod. This over here, but obeying these rules. Only one disc may be moved at a time. Each move consists of taking the upper disc, one of the rods, and sliding it to another rod on top of the other discs that may already be present on the rod, but no disc may be placed on top of a smaller disc. That's tough. So you put this one over here, you put this one over here, and then you put that one over there, and then you put this one over here. You see there's a way to do this as an algorithm. So you can see for, say, 4 discs, you move this one over here, you move this one over there, and then the next step over here is this one over here, after we've moved this over here. And all of a sudden we get to this stage right here, okay? We get to this stage where we have this solution in terms of a smaller set of itself. Okay, so this is the nth case. This is the n minus 1th case plus 1. Okay, so so you do this process all over again. So it's an intermediate step to get to this n minus 1th case, and then you just move this thing over and you just do the inverse of what you did here. So we're inferring that this is an hn equals hn minus 1 plus 1. I think that is the thing that we assume here. So here we go. We're looking at it. Yes, hn equals 2hn plus 1. So we reduce it to this stage right here. This is hn. This is h meaning the number of moves. And this is hn minus 1 plus 1, okay? And we have to do this again, so it's 2hn plus 1. So here, this is the hn plus 1 case. This is the hn minus 1 case. This is the hn minus 1 plus 1 case. And this is the doing it all over again. You do this hn minus 1 again, so it's 2hn minus 1 plus 1. So that is, we're assuming this open form expression. Now we're going to use iteration. This is what iteration is. Hn equals 2hn minus 1 plus 1. So I put in 2hn minus 2 plus 1 for hn minus 1. Okay, we substitute smaller versions of itself in all the way through and keep going until we arrive at this final solution, 2 to the n minus 1. So this is what we inferred, and that's the open form expression, because this is based on a recursive set. And this is a closed form expression, okay? So we've reduced or iterated from our hypothesized solution to the problem by looking at this particular set, coming up with this pattern. You know, this pattern, h of n plus 1 plus 1, and we do the h of n minus 1 twice, okay? And then we use iteration to come at a closed form solution. Is this correct? We still don't know if it's correct. all we did is hypothesize this open form expression, then iterated to this closed form expression. So never mind that. So the proof is very simple. Proof by mathematical induction, basis step, n equals 1. Well, h1 equals 1 equals 2 to the 1 minus 1. So that's okay. So we're looking at this right here. So 1 equals h1 equals 1, which is this thing here, hn equals 1. So hn equals 1, because that one doesn't exist, okay? That's like h sub 0, okay? So h1 equals 1, and the right side, 2n minus 1 is 2 to the 1 is 2 minus 1, so yes, the basis step works. Now, we derive the n plus first step. We assume the inductive hypothesis that hn plus 1 equals 2hn plus 1, and we put in the inductive hypothesis is by assuming that this closed form expression is true. And 2 times 2 to the n is 2 to the n plus 1, minus 2 plus 1, which is the final form we were trying to arrive at. That's the nth step, or sorry, the k step. This is the k plus first step. That is the easiest proof by induction you will ever see. So that solves the Tower of Hanoi. I can't talk. So, how many discs to move? 64 discs, which was what the king way back when of some country proposed to one of his scholars. And how long would it take to do that? If you could do one disc at a time, it would take that many years, 10 to the 19 years. 10 to the 19 years. So this problem scales exponentially, as you can see here. 2 to the n, it's exponential. I think the original question was here. Oh, wait, I don't state it anywhere of why it's 64 discs, because that's the original way it was stated hundreds of or many centuries ago. Okay, recursion. We see how principal mathematical induction lends itself naturally to recursion. We can see that recursive sets can be proved, they're closed form expressions by mathematical induction. Also, some programs are recursive, and therefore you can use mathematical induction to prove them correct. But this just is so limited. This is formal methods in computing science. There's a course in third year, I believe it's third year, maybe fourth year, on formal methods. But it's very restricted, the kinds of proof techniques that you can use. Clearly, a recursive program can be proved by mathematical induction. Proved correct. That's pretty cool. We already did this. I don't know why that's still there. Okay, you can look at it again. That's the end of recursion. This is just a more detailed look at how to do that visual problem. Okay, that means I'm going to take this out of the previous set. I have to fix the inductive how you say in English, the inductive, I have to fix the inductive PDF, and I'll send that to you as soon as I finish doing that. Anyway, good luck on the exam. It's just 6 days away. It's Tuesday right now, my time, February 3rd. On February 9th, we will meet in AQ 3181 at 3:30 p.m. It's going to be a 50-minute exam. We've already gone over it. We did the review, and I wish you all the best of luck. You can email me anytime, during business hours. Expect to get a response then. I responded to someone last night at 3 a.m. Thank you, that person that posted that. Apparently, I didn't make it visible. The week 4 videos, I didn't make them visible to the class. I forgot to hit that toggle switch, and I woke up at 2:30 like I do every night, and I took care of that. So, okay, people, like I said, the very best of luck. I want you all to do well. I really think that you're going to do well. I think this is an easy test, and as long as you've listened to what I've been talking about and emphasizing. So, until Monday, toodaloo.